Hiya, I'm Barnaby. I'm the team lead for the Testing My Patients team here at Strathsteads, and I'll be taking you through our manufacturing review for the National Rocketry Championship this year. Our mission statement is to advance our aerospace and engineering knowledge through the collaborative design, build and launch of a mid-power rocket to 2,500 feet, offering as much hands-on experience in rocketry and electronic systems as we can, while having a major focus on interdisciplinary teamwork. As part of our broader certification effort, we'll be rigorously testing our flight computer Firefly Ultra, enhancing our team proficiency and preparing for our future challenges. Our objectives are exactly the same as they were in the critical design review: to design, construct and launch a rocket capable of 2,500 feet, to design our flight computer Firefly Ultra, to detect altitude, position, acceleration and orientation, as well as fire ejection charges at the appropriate stages of flight, and to test the ease of operation of Firefly Ultra in a high-stress environment. Here's a look at our timeline for the project. The major change since the critical design review here is the removal of sensor fusion. This algorithm will not be prepared for the flight, so we will instead use this flight as a data gathering exercise. And finally, our budget is the same as in the critical design review. The only change here is the addition of the BMFA memberships at £49 per person. This brings it to a total of £147 for the 3 memberships we need to cover our 15 planned attendees. I'll pass over to the rest of the team to cover the current state of manufacture.
This is the wiring harness design for the rocket. We are using RS Pro 2.6 amp hour 18650 batteries, which have a nominal voltage of 3.7 volts and are lithium ion chemistry. We have one dedicated for the customer payload to meet the voltage, power and lifetime requirements, and we are using an XT30 connector as required by the interface. We have a shared battery for the rideshare payload, so our Firefly Ultra that we're developing ourselves, and our COTS reference Easy Mini. These will be connected to LEDs to show their pyro state, and we have individual commercial off-the-shelf screw switches to control power and our pyro enable for our SRAD board.
Now onto the launch vehicle manufacture, starting with the motor retainment. First, the centering rings were epoxied to the motor mount tube, threading the shock cord through the top ring with enough cord to be wrapped around the motor mount tube 6 times. The top centering ring was positioned so that in the worst case scenario, a second shock cord could be attached to the top, above the centering ring. The positions of the rings have been slightly moved since CDR. These changes have been reflected in the open rocket. The shock cord was then wrapped around the motor mount tube 6 times and epoxied in place. The epoxy was then applied to the edge of the centering rings and inserted at the correct distance into the aft coupler. Extra epoxy was added around this assembly for structure support. Finally, the lower motor mount tube and bottom edge of the coupler were coated in epoxy before being inserted into the fin can. This system allows for the motor to be retained, as shown in the video here. The 3D printing retaining ring squishes the motor between it and the motor mount tube. We have several main structures, such as the airframe and nose cone, that needed to be manufactured. We bought phenolic airframe from Black Cat Rocketry and cut it to size. Unfortunately, they were out of coupler, so we reinforced a cardboard tube with laminating epoxy. This was tested to the same standards as the phenolic. This will be shown later in the testing section. The nose cone and fin can were 3D printed, sanded, and filler primed. They were sanded again until they were smooth. The AV airframe and coupler were glued together, ensuring there was at least 1 diameter of coupler on each side. The outer rocket was then primed and ready for painting, ensuring that all coupler has at least 1 diameter of overlap. For the recovery system, the rocket uses motor ejection to deploy a single parachute. It's not going fast enough to need a drogue chute. The Kevlar shock cord attaches to the motor mount tube and threads through the top centering ring, where it has been epoxied, as shown here and in the earlier slide. Then it is threaded through the rear parachute bay and connected to the AV bay using a quick link. The parachute and a Nomex fireproof blanket is attached to the shock cord with a quick link, approximately in the middle from the top of the parachute bay to the bottom of the AV bay. Currently, the rocket does not have holes for pins, so we cannot test it properly.
We have made a revision to the avionics bay and it fits correctly within our airframe. Initially, was the space in the bottom to fit the U-bolt was incorrect and would not allow for the bulkhead to be correctly fitted in. The holes in the bottom of the airframe will be lined consistently with the thread insert holes in the avionics bay in order to ensure that both holes are correctly aligned along the length of the rod.
The launch vehicle adapter is compatible with the new version 2 of the customs payload and attaches forwards of the avionics bay through the same threaded rods that the entire avionics assembly is held together.
The rideshare payload is still in the final stages of design. We are conducting internal reviews for our right first time design approach, as we don't want to have a second revision for NRC. We are using the development board to identify issues, and we are intending to order before the end of April.
The following slides will very briefly go over the changes in our open rocket model since the CDR. New simulations show that our apogee will be anywhere between 380 meters and 420 meters, depending on the wind speed. This is significantly higher than CDR. In addition, our stability now does remain within a range between 1.5 and 2.5 calibers. In fact, that's always between 2.2 and 2.5. And finally, in the worst case scenario, we're estimating about 360 meters of drift downrange.
A major review has been completed on the state of schematic design. The majority of issues are low priority, having little to no impact on the functional performance, and the priority is on fixing all of the identified high priority issues. The remaining major issues are that the magnetometer requires an LDO to convert the 3.3 volts to 1.8. The GPS backup battery power circuit still needs to be fixed. An OR gate has been added to the high range low precision accelerometer to prevent bus collisions. And the VBAT and USB 5V connections still need to be sorted out. In terms of the PCB, it is in process of writing and is pending revision based on the internal review findings. In terms of schematics, the sheet and subsystems are largely the same as the development board, but have been updated based on testing.
This shows the current state of our Ultra ground station. The current PCB needs further review, as well as the schematic. The design is building on previously used components such as the MCU and the radios, so this should need minimal development. And we include a e-ink display for showing the current status of the flight from our SRAD board, as well as an 18650 mounted directly for power, and a GPS for both getting the location of the ground station and for time division multiplexing synchronization. We have up to 4 radios for frequency division multiplexing, and we can show data either on that display, or it can be shown via that USB-C cable and connected to a laptop.
These slides show an updated requirement compliance analysis since the critical design review, showing both the requirements provided by you as well as our own internal requirements. Please pause at any point to take a read, otherwise we'll go straight on to testing.
In order to test the alignment of our fin can, we suspended a plumb bob from each fin in order to ensure that there was a straight vertical line down the entire surface. There was no obvious cant to either fin, which was to be expected, as the entire fin can had been 3D printed. In order to proceed with the longitudinal loading test of our fin, we calculated the maximum acceleration of our rocket using the open rocket model and the measured mass of the fin. This resulted in a test force of approximately 4.5 newtons, meaning that we'll applied a load of 0.5 kilograms to the fin tip. There was no obvious breakage or deflection to the fin during this testing. We then applied a lateral load to the fin. The launch weight of the fin is 1.2 kilograms, and the equivalent weight which we applied was 1.255 kilograms. The fins experienced a deflection of under 10 degrees, meaning they were well within parameters. We then applied an axial load to the airframe and aft section of the rocket. The maximum load which it will experience during flight is roughly 25 kilograms, which we applied. No deformation of either section was visible during this testing.
Firefly Ultra is using screwless terminal blocks. We are using these Phoenix Contact 8-pin terminal blocks. And what we really wanted to test here is if they're going to hold up to the rigors of flight and not release the wires under high shock loads. So for this purpose, we have developed the PCB Shock and Mechanical Acceleration System for Harsh Environment Replication, or PCB Smasher. Initial tests with development boards indicate that they will meet requirements. You can see one of our tests here, where we're using slingshot bungee to accelerate the board into a hard stop. And we're going to do further tests with an IMU to find those peak forces. Our requirements say that we should have up to 100 G of shock, so very, very short impulse forces, and up to 50 Gs of sustained accelerations. So our intention with this device is to get really, really hard accelerations using the bungee, and then those shock forces as it stops. And we can rotate that development board as we want to test it in all orientations.
Some of the tests that we've performed for the sensors on Firefly Ultra. For the barometer, we've got a vacuum chamber. We've tested that it's working and holds a vacuum. We've not yet tested with the sensors inside. However, we have performed some basic functional testing for the altimeters and have confirmed that they do work. So similarly with the GPS, we need to do some further testing to get numbers for the time to fix and the positional accuracy, but we have confirmed that the chip is working. And same story with the IMU. We've got functional testing done, but we need to get some more numbers. Cool. So over here we see the functional tests for the altimeter and the IMU. So as you can see, as I take the board up and down the frame, the graphs update, and as I shake it around, the little torus spins.
Here's an updated risk assessment for the project. We've added one risk since the CDR, that is a misalignment in holes in the airframe. In addition, we've added post-mitigation likelihood and severity scores.
Painting, holes for the customer payload, and the fuselage stiffness test. We're waiting until we have the internals completed before we start drilling holes in the external of the rocket. The fuselage stiffness can't be done until holes are drilled, parts are pinned, and also the final centre of gravity is found.
Our next steps for the rideshare payload are to finish the PCB designs, review and revise the designs, order the PCBs and assemble them, and then we are to continue with the individual component testing with the development board and integration testing with the final boards.